Assalamualaikum and hello everyone. Today we're going to look at topic 9, kinetic theory of gases and thermodynamic. Okay, first we look at topic outline. There is 5 subtopic for this chapter. Okay, first 9.1 kinetic theory of gases, and then 9.2 molecular kinetic energy and internal energy, 9.3 first law of thermodynamic, 9.4 thermodynamic process, and 9.5 thermodynamic work. Okay, first we look at learning outcome for 9.1 kinetic theory of gases. So at the end of this topic, you should be able to first state the assumption of kinetic theory of gases. B, describe root mean square RMS speed of gas molecule. Okay, C, solve problem related to root mean square speed of gas molecules. D, solve problem related to the equation P is equals to 1 over 3 nm Vrms squared and pressure P 1 over 3 rho V RMS squared. Okay, kinetic theory of gases. The macroscopic behavior of an ideal gas can be described by using the equation of state, but the microscopic behavior only can be described by kinetic theory of gases. So in order for us to use kinetic theory of gases, there is few assumptions that we need to take consideration. Okay. First, all gases are made up of identical atoms or molecules, and then all atoms or molecules move randomly and haphazardly, and then the volume of the atoms or molecules is negligible when compared with the volume occupied by the gas. Next, the intermolecular forces are negligible except during collision. Okay, next, interatomic or molecular collision are elastic. Okay, next, the duration of collision is negligible compared with the time spent traveling between collision. And lastly, atoms and molecules move with a constant speed between collision. And gravity has no effect on molecular motion. So all these assumption kita kena consider lah before kita guna theory kinetic theory of gases. Okay, and then we look at force exerted by the ideal gas. So this is the derivation of the formula. Okay, you can check this by yourself. So the force is given by formula N over 3 m mean V squared over D. Okay, so kita panggil mean square velocity. Okay, the symbol is mean square velocity. And then pressure of an ideal gas. Okay, since kita ada definition of pressure, P is equals to F over A, and A is equals to D squared, and F is equals to N over 3 m mean V squared over D. So kita akan dapat PV is equals to 1 over 3 nm mean V squared. Okay. Next, since we have density rho is equals to nm over V, kita boleh substitute. Okay, dan kita akan dapat P is equals to 1 over 3 rho square mean V squared. Okay, ataupun mean square velocity. Next, we look at root mean square velocity, VRMS. Okay, so basically VRMS is this one lah. Kita ada, we have root. So this is root. Okay, then we have mean. Okay, then we have square. Okay, so that's how we get our name lah. Root mean square. Okay. So from the equation of state in terms of Boltzmann's constant, so we have PV is equals to NKT. Okay, so by equating the equation 9.4 and 9.2, we will have NKT is equals to 1 over 3 nm mean square velocity. Okay, so we have mean square velocity is equals to 3 kTm. So kita square root kan dia, we will have a VRMS ataupun root mean square velocity is equals to square root 3 kT over m. Or Vrms is equals to square root 3 RT over m. So you have to use this equation a lot for Vrms. Okay, so Vrms is root mean square velocity. It is a speed. Okay, and then m is mass of molecules. Okay, capital M is molar mass of gas, and T is absolute temperature. Okay, next C, pressure of an ideal gas. Okay, since PV is equals to 1 over 3 and mv Rms squared, and P is equals to 1 over 3 rho V Rms squared, so thus, okay, mean squared velocity is which equals to Vrms squared equals to 3P over rho. Okay, so we'll have this one lah. So Vrms, kita square rootkan dua-dua lah. Sebab kita nak Vrms saja. Okay, we will have Vrms is equals to 3 square root 3P over rho. So first we look at example 1. So 8 gas molecules chosen at random are found to have speed 1, 1, 2, 2, 2, 3, 4 and 5 meter per second. Determine the mean speed of the molecule. So mean is average. So we just find the average lah. So we just add all the velocity divide by 8 because we have 8 molecules. So 1 plus 1 plus 2 plus 2 plus 2 plus 3 plus 4 plus 5 divided by 8. We're going to have 2.5 meter per second. Okay, next we want to find the mean square speed of the molecule. So again, mean is average, okay, but this time they want you to find mean squared. So we just square everything lah. So 1 squared plus 1 squared plus 2 squared plus 2 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared divided by 8. So you have mean square speed equals to 8 meters squared per second negative 2. Okay, sebab kita squarekan dia, so unit pun squared lah. And lastly, they want you to find the root mean square speed of the molecule. So all you have to do is square rootkan sahaja. Okay, so you have square root of 8, you get 2.83 meter per second. So next example number 2, a cylinder of volume 0.08 meter cube contains oxygen gas at temperature of 280 Kelvin and pressure of 90 kilopascal. Determine the mass of oxygen in the cylinder, the number of oxygen molecules in the cylinder, and the root mean square speed of the oxygen molecules in the cylinder. Okay, so first they nak cari mass of oxygen. So by using equation of state, we will have PV is equal to nRT and N is equal to M over M. Okay, so we will have PV is equal to M gas divided by molar mass M RT. So masukkan saja nilai. Okay, so you have M gas is equal to 9.9 times 10 to the power of negative 2 kg. Next, they want you to find the number of oxygen molecules. Okay, so number of oxygen molecules N. So we know that we have two equations. Okay, N is equal to M gas over M and N over NA. NA is number of Avogadro number. Alright, so again, you just substitute the value. You will have N, the number of molecule is 1.86 times 10 to the power of 24 molecules. Okay, last they want you to find root mean squared. So just put the equation square root Vrms equals to square root 3RT over M. Okay, substitute the value and you will have 467 meter per second. So this is the exercise that you can do to check your understanding on topic 9.1. Next, okay, we're going to look at topic 9.2, okay, molecular kinetic energy and internal energy. So learning outcome, at the end of this topic, students should be able to A, Explain and use translational kinetic energy of a molecule. Okay. B, define degree of freedom. Okay. C, identify number of degree of freedom. F for monoatomic, diatomic and polyatomic gas molecule. D, state the principle of equipartition of energy. E, discuss internal energy of gas. And F, solve problem related to internal energy. Okay. So first we're going to look at A, translational kinetic energy. Okay, so again, this is how you derive the equation. Okay, we're going to have P is equal to 1 over 3 nm over V mean squared velocity. And then P is equal to, okay, we rearrange the equation. We will have P is equal to 2 over 3 N over V 1 over 2m mean squared velocity. Okay, so we know that P, pressure, will increase when N over V increases, and also half mv squared increases. Okay, in another word, N over V is number of molecules per volume, and also half mv squared, okay, is kinetic energy lah. So we can rearrange our equation. Okay, PV is equals to 2 over 3n half m mean squared velocity, and PV is equals to nkt. Okay, so we will have to substitute the equation, and we will get KTR is equals to 3 over 2 KT, and okay, 3 over 2 R over NAT. Okay, so KTR is average translational kinetic energy of a molecule. T is absolute temperature, K is Boltzmann constant, R is molar gas constant, and Na is Avogadro constant. So, for n molecules of an ideal gas in the cubical container, the average or the mean translational kinetic energy E is given by E is equals to 3 over 2 nkt, or E is equals to 3 over 2 nRT, depending on the information given in your question lah. You can choose either nkt or nRT. Next, degree of freedom. So, degree of freedom is defined as the number of independent ways in which an atom or molecule can absorb or release or store the energy. Okay, so number of independent ways. Okay, our symbol is F lah. Okay. C, number of degree of freedom F for monoatomic, diatomic and polyatomic gas molecules. Okay, so for monoatomic gas, okay, the number of degrees of freedom is 3. Okay, 3 direction of translational motion will contribute translational kinetic energy as shown in figure 9.3. So we can see for monoatomic gas, it can move, okay, in 3 direction lah, Vx, Vy and also Vz. So the degree of freedom is 3. Next, for diatomic gas, okay, example H2O2 or N2, the number of degree of freedom is, okay, 5. Why 5? Because okay, you can see in the picture, figure 9.4. Okay, of course, it can have 3 translational kinetic energy, Vx, Vy and Vz, but it can also have 2 rotational kinetic energy, as you can see here. Okay, it will rotate at Z and also Y. Okay, it won't rotate at X, Y because tak ada, dia akan rotate setempat je kalau macam tu kan. So that's why we have 5 degrees of freedom for diatomic gases. Okay, later in the question they will give you type of gases, so you need to identify, is that monoatomic gas, diatomic gas or polyatomic gas. Okay, so you can check this one lah, try to memorize it. Okay, next polyatomic gas. Okay, example is H2O, CO2 and H3. Okay, so the number of degree of freedom is 6. Okay, where 3 come from translational kinetic energy, of course Vx, Vy, Vz, and then another 3 come from rotational kinetic energy. It will rotate in x direction, y direction, and also z direction. So the number of degree of freedom for polyatomic gas is 6. Okay, so you can see here monoatomic gas, example He, translational 3, rotational 0, so total 3. So formula ataupun average kinetic energy per molecule is 3 over 2 kT. And then diatomic, example H2, okay, translational ada 3, rotational have 2, so total is 5. So your formula will become 5 over 2 kT. And lastly, okay, polyatomic, okay, example H2O, translational have 3, okay, rotational have 3, so total is 6. So your formula for average kinetic energy per molecule is N over 2 kT or 3 kT. Okay. Next, degrees of freedom depends on the absolute temperature of the gases. Okay. So hydrogen gas have the vibrational kinetic energy as shown in figure 9.6, where contribute 2 degrees of freedom, which correspond to the kinetic energy and the potential energy associated with vibration along the bond between the atoms. When the temperature is around 250 Kelvin, monoatomic kita ada 3 degree of freedom, diatomic 3, polyatomic pun 3. Okay, untuk temperature between 250 and 750 Kelvin, okay, monoatomic have 3 degree of freedom, diatomic have 5, and polyatomic have 6. But for a higher temperature, which is more than 750 Kelvin, monoatomic still have 3, but diatomic will increase to 7, and polyatomic will increase to 8 degree of freedom. Okay, next, principle of equipartition of energy. Okay, so you highlight the word equipartition. Okay, it means equal. Okay, it states that the mean average kinetic energy of every degrees of freedom of a molecule is half kT. Okay, so K ataupun the mean average kinetic energy, okay, is equals to F over 2 kT. Okay, mean average kinetic energy per molecule. Or you can also use F over 2 RT. Depends on the information given in your question. Okay, either they give you K or R. So next we look at example number 3. A vessel contains hydrogen gas of 2.2 times 10 to the power of 18 molecules per unit volume. And the mean square speed of the molecules is 4.5 km per second at a temperature of 50 degrees Celsius. Determine the average translational kinetic energy of a molecule for hydrogen gas, and B, the pressure of hydrogen gas. So, for A, kita nak cari average translational kinetic energy. So, we can use the formula KTR is equals to 3 over 2 KT. Okay, so just substitute the value. K is 1.38 times 10 to the power of negative 23. And their temperature is 3 to 3.15 Kelvin. So, you will get translational kinetic energy 6.69 times 10 to the power of negative 21 joule. Next, you want to find the pressure of hydrogen gas. So you know that formula for pressure is 1 over 3 N over Vm, okay, mean squared velocity. So you rearrange the equation, okay. So you substitute M with M over Na. So you will substitute the value and you will get P is equal to 1.1 times 10 to the power of negative 5 Pascal. Okay. Right. Next, example number 4. A vessel contains an ideal polyatomic gas at temperature of 30 degrees Celsius. The total translational kinetic energy of the gas molecule is 6 times 10 to the power of negative 6 joule. The mass of the gas is then doubled and the total translational kinetic energy of the molecules become 13 times 10 to the power of negative 6 joule. Determine the new temperature of the gas. Okay. So, dia nak suruh awak cari new temperature. Okay. By applying the equation of total translational kinetic energy, we have E is equals to 3 over 2 NKT, where N, number of molecule, is M over M times NA. Okay. And K is equals to R over NA. So, you rearrange your equation, you will get 3 over 2 M over M, molar mass, okay, RT. So, substitute the value, okay. For temperature T1, you will have E1 is equals to 3 over 2 M1 over M RT1. And then T2 is E2 is equals to 3 over 2 M2 M over RT2. Okay. So, you will have E2 is equals to 3 over 2 2M1 over MRT. Okay, you just substitute M2 is equals to 2M1. Okay, as given in the equation. Okay, now you can equate this equation. Okay, E2 over E1 equals to 2T2 over T1. Okay, you just divide equation 2 with equation 1. Okay, then you just substitute the values. You will have T2 is equals to 328 Kelvin. Next, E, internal energy U. Okay, internal energy is defined as the sum of total kinetic energy and total potential energy of the gas molecules. But in ideal gas, the intermolecular force are assumed to be negligible. Thus, the potential energy of the molecules can be neglected. Thus, for N molecules, U is equals to F over 2 NKT, or U is equals to F over 2 nRT. Okay, remember F is degree of freedom. Okay, so table 9.2 shows the properties for one molecules of an ideal gas. So, monoatomic, degree of freedom dia 3, diatomic 5, okay, polyatomic 6. So, average kinetic energy per molecule is 3 over 2 kT for monoatomic, okay, 5 over 2 kT for diatomic, and 6 over 2 kT or 3 kT for polyatomic. And then internal energy U per mole is equals to 3 over 2 RT for monoatomic, 5 over 2 RT for diatomic, and 6 over 2 RT or 3 RT for polyatomic. Okay, you can memorize this equation. Last, example 5, 2 moles of either monoatomic gas is, 2 moles of an ideal monoatomic gas in a closed container at constant volume is heated until its pressure is doubled. Okay, the pressure is doubled lah. So, kita boleh kata P2 is equals to 2P1. Here. Okay. If the final temperature of the gas is 750 Kelvin, calculate the initial temperature of the gas. So, we want to find T1. And then B, the change of internal energy of the gas. Okay. So, kita apply Gay-Lussac law. Okay. P1 over T1 equals to P2 over T2. So, we just rearrange. Okay. And we know that P1 is equals to, P2 is equals to 2P1. Okay. So, we substitute the value. We have T1 is equals to 375 Kelvin. Next, we want to find the change of internal energy. So, change is delta. Okay, so we want to find delta U. Okay, So delta U is basically U2 minus U1. So in this case, F2 nRT2 minus F2 nRT1. Okay. So we can substitute the values. We just minus 750 with 375. Okay, you're going to have delta U is 9.35 times 10 to the power of 3 joule. So that is the internal energy. Change in internal energy. So this is exercise for subtopic 9.2. Okay, please try this exercise in order for you to check your understanding in this subtopic. Next, we're going to look at 9.3, First Law of Thermodynamic. So the learning outcome at the end of this topic, you should be able to A. State First Law of Thermodynamic. Okay. B. Solve problem related to First Law of Thermodynamic. Okay. First Law of Thermodynamic. First Law of Thermodynamic. Sign for heat Q and work W. Okay. Sign convention for heat Q. Q positive values. Heat flow into the system. Okay. If you have positive Q, then it means heat flow into the system. If Q have negative values or negative Q, heat flows out of the system. Okay. And then sign convention for work again, W positive, work done by the system. W negative, work done on the system. Okay. So you can highlight the verb into and out, here, by and on the system. Okay, so that is the difference. Okay, so figure 9.7 shows the thermodynamic system may exchange energy with its surrounding environment. So surrounding environment, kemudian system. Look at this one. Okay, if, okay, this one Q is bigger than 0 or positive Q. Okay, energy is flow into the system. Okay, kalau Q awak less than 0 or negative values, okay, energy flows out, okay, of the system. Okay, for C, okay, if we have Q0 and W is bigger than 0 or positive W, you can see that, okay, energy, okay, is out of the system. Okay, again this one, okay, if your W is negative values, energy flows into the system. Okay, alright. For E, okay, if Q is bigger than 0, W is bigger than 0, okay, you can see lah. Okay, and this one is situation kalau Q is less than 0, W is less than 0. Okay, next. So example for work done by the system and work done on the system. Okay, you might get confused. What does it mean by work done on the system or by the system? Okay, so look at this piston. Okay, this is the initial situation. We have that much of air. Okay, if you have expansion, you're gonna have column dia lagi besar lah. Okay, kemudian kita ada compression. Okay, the column is smaller. So when the air is expanded, the molecule loses kinetic energy and does positive work on this piston. So when the air is compressed, the molecule gains kinetic energy and does negative work on the piston. Next, first law of thermodynamic. Okay, so first law of thermodynamics states the heat Q supplied to a system is equals to the increase in the internal energy delta U of the system plus the work done W by the system on its surrounding. Ataupun kita boleh kata Q is equals to delta U plus W. Okay, or delta U is Q minus W. Okay, so this is the equation. So this is a very important equation because you're going to use it a lot in this chapter. Okay, where Q is quantity of heat supplied, W is work done, delta U is change in the internal energy, U1 is initial internal energy, and delta U is final internal energy. So in this equation, the positive and negative values for Q and W is very important. Awak salah masukkan sign, then you're going to have a wrong answer lah. Okay, so it's important for you to identify is Q positive or negative. Is W is positive or negative. Okay, later we will do some example to check on that one. And then for infinitesimal change of the energy, okay, very small change lah. dQ is equals to du plus dW. This is a very small change. Okay, the first law of thermodynamics is a generalization of the principle of conservation of energy to include energy transfer through heat as well as mechanical work. So the change in the internal energy delta U of a system during any thermodynamic process is independent of path. For example, a thermodynamic system goes from state 1 to state 2 as shown in figure 9.1. Okay, so there is a lot of process lah from 1 to 2. So figure 9.9, so kita boleh kata kalau dia follow path yang colour merah tu, if it's follow the red path, delta U 1 to 2 is equals to delta U 1 to 4 to 2, the green path, okay, equals to delta U 1 to 3 to 2. Okay, that 1 to a blue path. Okay, so this is the initial position, this is the final. Even though it use a different path, you will have same change on U. The internal energy depends only on temperature of the system. If the initial and final temperature state of the system is the same, hence delta U is equals to U2 minus U1, which is equals to 0. Okay, kalau sama, initial and final temperature is the same, then delta U equals to 0. So the change in the internal energy is also 0 in the cyclic thermodynamic process because the initial and final state of the system is the same. Okay, so the internal energy is not depends on the volume of the system. So next we look at example number 6. Okay, we have 2,495 joule of heat is used to heating a mole of neon gas from 27 degrees Celsius to 147 degrees Celsius at constant pressure. Determine the change in internal energy of the gas and the work done of the gas. Okay, so we want to find the change in internal energy. So we use delta U is equal to U2 minus U1. So just masukkan sajalah. U2 is F over 2 nRT2 minus F over 2 nRT1. So we can say delta U is F over 2 nRT2 minus T1. So this is a neon gas. Okay, so neon gas is monoatomic, so our F is equals to 3. So just substitute the value, 3 over 2, 1, 8.31, 420 minus 300 Kelvin. So our change in internal energy, delta U is 1,496 joule. Okay, for B, we use Q is equals to delta U plus W. Okay, we know that Q is given 2,495 equals to 1,496. This one you find in A plus W. So rearrange, you will get W is equal to 999 joule. Okay, next, 9.4 thermodynamic process. So for learning outcome at the end of this topic, you should be able to define the following thermodynamic process. Okay, kita ada 4: isothermal process, isochoric process, isobaric and adiabatic. And B, analyze PV graph for all the thermodynamic process. So thermodynamic process, there are 4 specific kind of thermodynamic process. It is isothermal process, isochoric or isovolumetric process. Okay, alert with this one, it has 2 names. Okay, isochoric or isovolumetric. It is the same thing. Okay. Alright, and then isobaric process and adiabatic process. So first, we're going to look at isothermal process. Okay, isothermal process is defined as a process that occurs at constant temperature. Okay, highlight isothermal. So the word thermal mean temperature lah dalam case ni. Okay, isothermal. So it has constant temperature. So when constant temperature, we know that delta U is equals to 0. This one kita tengok tadi, right? If there is no change in temperature, then delta U is equals to 0. So our equation, Q is equals to delta U plus W. Okay, since delta U equals to 0, we have Q equals to W. Okay, so for isothermal process, Q equals to W. Why? Because delta U equals to 0. So isothermal change, okay, when a gas expand or compress isothermally, okay, dia berubah tetapi temperature tidak berubah lah, constant temperature. So we say that PV is constant. Okay, so if PV is constant, we're going to say P1 V1 is equals to P2 V2. Okay, first situation equals to second situation. Okay, if the gas expand isothermally, thus V2 is bigger than V1. If the gas compress isothermally, V2 is smaller than V1. Okay, so expand, bila dia expand, W positive. Okay, we have positive W. If it is compressed, W is negative. So you have to memorize this one. Okay, remember, expand W positive, compress W negative. Next, isochoric process or isovolumetric process. Okay, you see that the word volumetric, that means it has the same volume. So isochoric or isovolumetric process is defined as the process that occur at constant volume. Okay, so volume tidak berubah. Okay, so you remember, if there is no change in volume, we can say W is equals to 0. Okay, W equals to 0 when there is no change in volume. So, our equation Q is equals to delta U plus W will become Q is equals to delta U sahaja. Kenapa? Sebab W equals to 0. Okay, when there is no change in volume, W equals to 0. Okay. In an isochoric process, all the energy added as heat remain in the system as an increase in the internal energy. Thus, the temperature of the system increase. Okay, so basically, kita just add up temperature lah. Kita increase the temperature. So, what happen is, dia akan increase temperature lah sebab volume tidak boleh berubah. Kalau volume berubah, dia boleh maintain the temperature lah. But in this case, our volume tidak berubah lah. So that's why. Alright, For example, heating a gas in closed constant volume container is an isochoric process. Okay, contohnya awak tutup satu bekas, what is it? Pressure cooker, right? You just give the extra energy atau heating, tetapi there is no change in volume. So what happened inside is the temperature inside is increased. Alright, next, isobaric process. Okay, so isobaric process is defined as a process that occur at constant pressure. Okay, kita ada constant pressure. Okay, we start with isothermal, constant temperature, isochoric, constant volume. So isobaric is constant pressure. So what happened is delta P equals to 0 and W is equals to P delta V. So our equation Q is equals to delta U plus W will become Q is equals to delta U plus P delta V. Okay. For example, boiling water at constant pressure is an isobaric process. Okay. So, remember this formula lah. Next, adiabatic process is defined as the process that occur without heat transfer into or out of the system. Okay, tak ada heat transfer. So, Q is equals to 0. So, kita boleh gunakan equation Q is equals to delta U plus W. Automatically, it's become delta U is equals to W. Okay, ataupun negative W. For example, the compression stroke in an internal combustion engine is an approximately adiabatic process. Okay. Note, for adiabatic process ataupun adiabatic expansion, V2 is bigger than V1, so W is positive value. But delta U is negative value, hence the internal energy of the system decrease. For adiabatic compression, V2 is smaller than V1, hence W is negative but delta U is positive values, hence the internal energy of the system increase. So you need to alert with this one. Okay, pressure volume diagram graph for thermodynamic process. So figure 9.1 shows a PV diagram for each thermodynamic process for a constant amount of ideal gas. Okay, so look at this one. Okay, path A, B. Okay, this one. I change the color to green lah. So this is A, this is B. Okay, so this path is isothermal process. Okay, there is change in P, there is change in V, but there is no change in temperature. So kenapa no change in temperature? You see lah, this red line is same temperature. T1, T2, T3, T4. Okay, this is the line for T4, this is the line for T3, this is the line for T2, and this is the line for T1. Okay, so the same line will have the same temperature. So if it is the line from A to B, okay, means there is no change in temperature. So that is an isothermal process. So later they will ask you to draw this diagram. Depending on the question, they might ask you to draw isothermal process or adiabatic process. Okay, you need to memorize how to draw this diagram. Okay, next, diagram A to C is the adiabatic process. So, from A to C, you can see there is some change in temperature. Okay, the temperature is changing. Okay. Next, from A to D, that one is an isochoric process. Okay, so isochoric process, nampak from A to D, there is no change in volume. Okay, the volume is V1 only. There's no change, but there will be change in pressure. Okay, and lastly, from A to E, isobaric process. Okay, there is no change in pressure. The pressure is only P1, but there will be change in volume. You have V1 and V2. Okay, one thing I forgot to mention for process, adiabatic process, okay, all will change. Okay, The temperature change, the pressure change, the volume also change. Okay. Adiabatic process, tiga-tiga nilai berubah. Okay, next. From the figure 9.1 ataupun 9.10, for comparison between the isothermal AB and adiabatic expansion AC, okay, the temperature fall Tc smaller than Tb, which accompanies the adiabatic expansion result in lower final pressure than that produced by the isothermal expansion. So Pc is smaller than Pb. Okay, the area under isothermal is greater than the area under adiabatic. Okay, i.e. more work is done by isothermal expansion than by the adiabatic expansion. Okay, next, the adiabatic through any point is steeper than the isothermal through that point. Okay, so you can compare lah proses-proses ini, apa yang lebih, apa yang kurang. Next, example 7. An ideal gas is contained in a cylinder by frictionless type piston. Okay, the cylinder is surrounded by insulation to prevent loss of heat. Initially, the volume of the gas is 2.9 times 10 to the power of negative 4 meter cube. Its pressure is 1.04 times 10 to the power of 5 Pascal, and its temperature is 314 Kelvin. Okay, calculate the number of molecules for the gas in cylinder. Okay, dia nak numbers of moles. Okay, B, the gas is then compressed to volume 2.9 times 10 to the power of negative 5 meter cube. Okay, highlight the word compress kat sini. Okay, and its temperature rises to 790 Kelvin. Determine the pressure of the gas after this compression. Okay, dia nak cari P. Next, the work done on the gas during the compression is 91 joule. Calculate the increase in the internal energy of the gas. So, increase, dia nak delta U. And explain why a rise in the temperature of the gas takes place during the compression. Okay, so solution by applying ideal gas equation. P1 V1 is equal to nRT1. Okay, substitute the values, you will get N is equal to 1.16 times 10 to the power of negative 2 mole. Okay, next, okay, nak cari P, right? Given V squared is equal to 2.9 times 10 to the power of negative 5 meter cube, and T2 is 790 Kelvin. Okay, kita apply P2 V2 is equal to nRT2. Okay, substitute the value, you will get P2 is equal to 2.63 times 10 to the power of 6 Pascal. Okay, kemudian given W is equal to negative 91 joule. Since the cylinder is fully covered by the insulator, no heat transfers. So Q equals to 0. Okay, so we can use Q is equal to delta U plus W, and Q is equal to 0, delta U kita nak cari, and W is negative 91. So we'll get delta U is equal to 91 joule. Last, okay, when the gas is compressed adiabatically, it does negative work. Okay, thus Q is equal to delta U plus W, and Q is equal to 0. So delta U is negative W. So the internal energy of the gas is increased to provide the necessary energy to do work. Since the internal energy is proportional to the absolute temperature, hence the temperature increase and resulting a rise in temperature. Okay, next we look at 9.5 thermodynamic work. So learning outcome, okay, at the end of this topic, you should be able to A, derive equation of work done in isothermal, isochoric and isobaric process from PV graph. Okay. B, solve problem related to work done in isothermal process. Okay. And isobaric process, isochoric process. Okay. Look at the equation. There is different equation for different process. So first we look at A, work done in thermodynamic system. Okay, consider the infinitesimal work done by the gas during the small expansion dx in a cylinder with a movable piston as shown in figure 9.11. So initially kita ada gas, okay, this is the initial situation. So this is the final situation. Okay, this one is the expansion lah. Okay, suppose the cylinder has a cross-sectional area A and the pressure exerted by the gas at the piston face is P. So the work done by the gas given by dW is equal to F dx cos theta, where theta is equal to 0. So dW is PA dx. So dW is P dV. Okay. In a finite change of volume from VI to VF, okay, so you have W is equals to integration of P dV, okay, where W is equals to work done, P is gas pressure, VI is initial volume, and VS is final volume. So for a change in volume at constant pressure, we will have W is equal to P delta V, which also means P is equal to PV finals minus V initial. So work done at constant pressure. For a process of this in the system which the volume is constant, okay, no change in volume, the work done is 0. Okay, right. So figure 9.12 shows the pressure P against volume V graph ataupun kita panggil PV diagram, where area under the PV graph equals to work done. Okay. So we have A, B, C and D. Okay. You can see that the work done, okay, for process A, initially VI, V final, okay, the direction is to the right, right? So your W is bigger than 0. We'll say that W is positive. Okay, but for B process, okay, dia gerak ke kiri, right? Okay, so that means the volume ataupun it is compressed. Okay, the volume decrease. Initial volume dia lagi besar daripada final volume. Okay, so your W is negative. Okay, so process C, you can see it has the same pressure, but okay, the volume is changing. So you can say W is PI VF minus VI. So your V is bigger than, so your W is bigger than 0. Or we can say positive values lah. Untuk process D, okay, there is no change in volume. Okay, isovolumetric, no change in volume. So bila no change in volume, okay, W is equals to 0. Okay, so that's how you look at your process and how you draw it. So you can see the area under the graph. So work done in isothermal process from the equation of state for an ideal gas, PV is equals to nRT, then PV is equals to nRT over V. Therefore, the work done in isothermal process which change of volume from VI to V final is given by, okay, W is integration from VI to VF of PdV. Okay, you substitute the values, you will have W is equal to nRT, integration of VI to VF of 1 over V dV. Okay, ingat because the integration of in terms of V, so we can put everything in front of the integration. Alright. So the final equation will be W is equals to nRT ln VF minus VI. Okay, next, for isothermal process, the temperature of the system remain unchanged. Thus, Pi Vi is equals to Pf Vf. Okay, so rearrange, we will have Vf over Vi equals to Pi over Pf. So, the equation, we can rearrange it, okay, in terms of P. So, we will get W is equals to nRT ln Pi over Pf. So, depending on the information given, either V or P, you can use different equation lah. Kalau your question given you the value of V, then you can use this equation. Kalau your equation give you the value of P, then you can use this equation. By applying the first law of thermodynamic, okay, Q is equals to delta U plus W. Ini equation yang paling banyak kita guna. Okay, you can rearrange that. Q is equals to nRT ln Vf over Vi ataupun nRT ln Pi over Pf. Okay. And then work done in isobaric process. Okay. The work done during the isobaric process with change of volume from Vi to Vf is given by W is equals to integration from Vi to Vf of P dV, where P is constant. Okay. There's V here. Okay. So, kita keluarkan P. We will have W is equals to P integration of dV. So, kita boleh dapat W is equals to P V final minus V initial, and W is equals to P delta V. Alright, so work done in isochoric process. Okay, so untuk isochoric process, there is no change in volume. So dV automatically equals to 0. Okay, no change in volume. Volume tidak berubah. So our W is equals to 0. Okay, because integration of P dV is 0. So look at example 8. Okay, we have this process A, B, C, D. Okay, a vessel contains an ideal gas in condition A, as shown in figure 9.13. When the condition of the gas change from A to B, the gas system absorbs heat of 2.55 kilojoule. Okay, they absorb heat. When the gas in condition B change to C, there is a heat transfer of 5.32 kilojoule into the gas. Okay, highlight the word into. Highlight the word absorbs. Okay. Calculate the work done in the process A, B, C. And then B, change in the internal energy of the system. The change in internal energy of the gas in process A, B, C. Okay, A, B, C. From A to B to C. Okay. The work done in the process CDA, okay, CDA, okay, and lastly the total amount of heat transfer from process CDA. So we do it one by one. Okay, so work done in the process ABC. So kita tengok work done dia, sebab dia daripada point A to point C ada dua proses, so you have to add one by one lah. So WABC is equal to WAB plus WBC. But WAB is equals to 0. Why? Look at here. AB, there is no change in volume. So, bila no change in volume, work kita 0. So, this one equals to 0. Okay. So, WABC is equals to WBC. So, just masukkan saja equation. PVC minus VB. Okay, PVC minus VB, you will get 1500 joule. Okay, next, by applying first law of thermodynamic for ABC, so QABC is equals to delta U ABC plus WABC. So, kita nak cari delta U, kita rearrange, kita akan dapat QAB plus QBC minus WABC. So WABC you have calculated before. It is 1,500 joule. So you just insert QAB dengan QBC. This both are positive because it is absorbed and flow into. Tengok balik soalan. Okay, dia kata absorb dan into, right? So they both is positive. So you will have delta U is equals to 6370 joule. Next, example 9. Tinggal something je. Okay, sorry. See the work done in the process CDA. So process CDA, as you can see before, from C to D and D to A. Okay, C to D, there is no change in volume. D to A, there is no change in pressure. So isovolumetric and isobaric process. Okay, work done again. WCD, there is two process, which is WCD and WDA. Okay, WCDA, there is two process in WCDA. First from from C to D, and then from D to A. Again, since there is no change in volume for process WCD, okay, so kita akan kata WCD is equal to 0. Okay, so this one is equal to 0. So you just look at WDA. So WDA, there is no change in pressure. So it is an isobaric process. So you can use equation PVA minus VD ataupun P V final minus V initial. Okay, so just substitute the value. You will have negative 1000 joule. Okay, of course it's going to be negative, right? Because the volume is decreasing, right? Look at this one. From D to A, the volume is decreasing. So, of course, you're going to have negative volume, negative value. So, it's negative 1000 joule. And then D, by applying first law of thermodynamic, okay, kita cari QCDA. Okay, just masukkan saja. Delta U CDA plus WCDA, and delta U CDA is equal to negative delta U ABC. Okay, so you just masukkan saja. You will have 7,370 joule. Okay, negative Look at this one. Sorry, one part. Okay, you can just use this one because values dia sama, cuma dia terbalik saja, so dia negative. And next, we look at example 9. A, write an expression representing the first law of thermodynamic and state the meaning of all the symbol. 2, the work done by an ideal gas at variable pressure. Okay, B, sketch a graph of pressure versus volume, okay, of 1 mole of ideal gas. Label and show clearly the 4 thermodynamic process. Okay, first law of thermodynamic, okay, kita tahu equation kita adalah Q is equal to delta U plus W, where delta U is change in internal energy, Q is heat transferred, and W is work done. Kemudian work done in variable process, so W is equal to integration from VI to VF of PDV, or W is equal to nRT ln VF over VI. Ni kalau kita dah integrate dia, ya. So this is the diagram that you need to memorize. Please memorize this diagram. So there is 4 process, okay. From A to B, that one is isothermal process. From A to C, that one is an adiabatic process. Okay, from A to D is isochoric process, and A to E is isobaric process. Okay, so boleh nampak lah. A to B, there is no change in temperature. Dia dekat temperature 2 sahaja. Okay, from A to C, semua berubah. Okay, temperature berubah. Nampak dia daripada T2 pergi T1. Okay, volume dia berubah. Okay, from VA to VB. Okay, and pressure dia pun berubah. PA to PB. Alright, for OA to D, okay, there is no change in volume, okay, but there is change in pressure. And last but not least, from A to E, isobaric process, there is no change in pressure, okay, tetapi volume dia berubah lah from VA to VB. Next, example 10, 1 mole of monoatomic ideal gas is at an initial temperature of 650 Kelvin, while the initial pressure and the initial volume are PO and VO respectively. At the beginning stage, the gas expands isothermally and cause its volume to increase to VO. That means the volume is doubled lah. Then the gas undergoes an isochoric process and returns to its initial pressure. Finally, the gas is compressed at constant pressure and returns to its initial temperature, pressure, and volume. Okay, first, A, sketch a graph of pressure versus volume for the whole process. And then B, by using the first law of thermodynamics, show that the total heat for the whole process is Q is equal to nRT ln 2 minus VVO, where N is the number of mole, R is molar gas constant, and KT is initial absolute temperature, and calculate the total heat for the whole process. And last, C, state whether heat is absorbed or released. Yang C ni, you just need to check it is positive or negative. Okay, so solution, okay, we have pressure, volume, and temperature. Initially, they say that the temperature is constant, so it is an isothermal expansion. Kemudian kata next it is an isochoric process, okay, where pressure is constant and volume is also constant. Okay. So for the isothermal expansion, P1 V1 is equals to P2 V2. So PO VO is equals to P2 V2 VO. Ini ada dalam soalan tadi kan, dia kata double. So P2 is 0.5 PO. Okay. For the isochoric process, P2 over T2 is equals to P3 over T3. Okay. So 0.5 PO over T1 is equals to PO over T3. So, kita rearrange, kita akan dapat T3 is twice T1. So, this is our diagram lah. So, from 1 to 2, it is an isothermal process. Okay. Kemudian, kita nampak from VO to 2VO. The volume is doubled. Okay. Kemudian kita pergi kepada isovolumetric. Okay. Isovolumetric. Okay. The pressure berubah. Okay. There is change in pressure from 0.5 PO to PO lah. Okay. And last but not least, it is 3 to 1. 3 to 1 is Isobaric process. Okay. Again, there is change in volume sahaja. Okay, for B, untuk isothermal expansion, awak just masukkan saja dalam equation kita. Q is equals to delta U plus W. But we know that delta U is equals to 0 for isothermal expansion. Sebab temperature kita sama, right? So, U kita sama. Sorry, U kita kosong. So, just masukkan saja W is equals to nRT ln P1 over P2. So, you just insert everything. You will have Q12 is equals to nRT ln 2. Untuk isochoric process, okay, from 2 to 3, we have delta U plus W. But since it is isochoric process, okay, there is no change in W. W kita kosong. Okay, sebab isochoric process means there is no change in volume. So, W is 0. So, just insert equation for U F over 2 nRT T3 minus T2. In this case, our F is 3. So just insert everything. You have Q23 is 1.5 nRT. For the constant pressure compression, okay, Q31, okay, delta U is equal to W. Okay, in this case, both value adalah. So 3 over 2 nRT T1 minus T3 plus P1 V1 minus V3. Okay, just substitute the values yang ini awak dapat tadi. So awak akan dapat Q31 is equal to negative 1.5 nRT1 minus POVO. So therefore, the total heat given is Q12 plus Q23 plus Q31. So tambahkan everything. So your final will be nRT1 ln 2 minus POVO. So the total heat, okay, just substitute the values. You will have negative 1658 joule. So since your Q is negative, okay, the heat is released ataupun flow out. Okay, sebab negatif. Positif bila dia masuk kan atau dia absorb. So since it is negative, the heat is released. Okay, next example 11. A 0.5 mole ideal gas is filled in 0.5 meter cube container of 30 degrees Celsius. The gas is isothermally compressed, okay, to a volume of 0.3 meter cube. So it is compressed. So, okay. So they compress at constant temperature. Okay, then the gas expand isobarically to its original volume. So, expand isobarically. Oh, sorry. Okay. A. Sketch a PV diagram these two thermodynamic process, and B. Calculate the total work done in the process. So initially P1, V1, T1, kemudian kita pergi kepada isothermal compression. So isothermal compression, kita akan dapat same temperature but we have different pressure and different volume. Kemudian kita pergi kepada isobaric expansion. So untuk isobaric, our pressure is the same. Okay, volume also the same, but our temperature will change. Okay, sorry, pressure is the same as P2, but volume is the same as V1. Okay, kenapa? Sebab dia back to its original volume. Okay, so that is how you get this situation. So of course, just like the example before, you need to find the P1 and also P2. Okay, just use P1 V1 is equal to nRT1. Kemudian P1 V1 is equal to P2 V2 untuk dapatkan P2. Okay, and lastly, we need to find our temperature 3, which is 505 Kelvin. Okay. So, we just draw it lah. Okay, first we have isothermal compression. So you can see the arrow is to the left. Okay, ke kiri. One thing you need to remember, when you draw or you sketch the diagram, the direction of the arrow is wajib. You have to draw the direction of the arrow because the direction will show it is compressed or expand. So that's why it is important for you to draw the arrow. So in this case, since it is compression, so it goes from bigger volume to smaller volume. Kemudian from 2 to 3 is isobaric expansion. So it goes from 0.3 to 0.5. Okay. So make sure you insert the value here. That's why it's important for you to find the P1, P2, V1, V2. And then B, the work done during the isothermal compression is given by W12 is equals to nRT1 ln V2 over V1. So you just substitute the values. You will get W12 is negative 400, negative 643 joule. Kemudian, next you need to calculate W23, okay. So since it is an isobaric process, so P2 V3 minus V2, so substitute the value, you're going to get W23 is 840 joule. So in order for you to find W123, you just add W12 plus W23. So you have 197 joule. So this is the exercise that you can do in order to practice more in this subtopic.